Catherine Meusburger. The diagrammatic calculus and three-dimensional sums in presence of defects. Thank you.
Thank you very much for the introduction. So in the course of this program, I've seen that there are really many phases, many phases where very similar structures come up that have, and one aspect of this is spherical fusion categories, bimodule functors, and bimodule natural transformations that come up on one hand in condensed matter physics, on the other hand in topological quantum field theories. And for this reason, I wanted to talk about diagrammatic calculus in the presence of defects. And I hope that to some degree everyone can see a little bit how this is connected. Okay, so the state sum models I want to talk about are Toraev-Viro, Barrett, Westbury state sums. And they can be seen as like a three-dimensional counterpart of models that are familiar from topological quantum computing and condensed matter physics. So more specifically, they're related to the Levin-Venn models and to Kitaev's quantum double models. So these models take a triangulated surface and then either a spherical fusion category, or if one wants to work with Hopf algebras, a finite dimensional semi-simple Hopf algebra. And out of this one can define some vertex operators and plaquette operators and a Hamiltonian. And as soon as you have a Hamiltonian, you have a ground state of the model. And the ground state of the model is specifically the vector space that the Toraev-Viro topological quantum field theory that can be realized as a state sum model would assign to the surface. Okay, so this is known. And the essential ingredient in this construction is sometimes called the F matrix and sometimes called the 6J symbol. I often say 6J symbol because I'm more used to it, but it's the same as the F matrix. And why is this so essential? It encodes the associator of the underlying spherical fusion category. And in a geometrical level, it encodes flips in the triangulation. So you have two adjacent triangles here, and you have two adjacent triangles here, and you flip the diagonal. And if you draw the dual graph of the triangle and label it with objects of the spherical fusion category, and then sum over simple objects, then you have the picture where you first fuse I and J to A, and then you fuse it with K, and then you make B. Or you could do it the other way around. You could first fuse J and K, so take the tensor product of J and K, then fuse them to C, and then take the tensor product with I and make B. And that's the connection between the associator of a spherical fusion category and the flips in the triangulation. And as we all know, there are also versions of Levin-Venn and quantum double models with defects. So I think the first work on this was by Kitaev and Kong, but there have subsequently been many other works that treat various types of defects in Levin-Venn and quantum double models. And the idea is then one needs some generalized data that labels the defects, and to encode the generalized the data for the defects in some generalized F matrices. So in a similar way as here the associator is encoded in the F matrix, one has some generalized F matrices that encode the additional isomorphisms, the coherence isomorphism of the defect data. And then one asks, of course, can this somehow be organized into a state sum model that really has defects of all codimensions, and what is the appropriate way also of treating this? And especially to show triangulation independence. Because if here the associator and the associated F matrix give you independence of the triangulation, then somehow in the presence of defects, this should be taken over by these generalized F matrices, and they should somehow enter in this picture. Okay, So to explain this, I'll start by explaining the Toraev-Vero-Barrett-Westbury state sums without the defects. So this is essentially a state sum model for a three-dimensional TQFT. And the ingredients in the state sum model are some oriented piecewise linear three-manifold and a triangulation. So the piecewise linear is not very important here, but one has to say with which type of three-manifold one wants to work. And it's triangulated. And the algebraic ingredient is a spherical fusion category. So that means it's a monoidal category, so it has a tensor product, it is rigid, it has duals. It's also supposed to be C-linear and abelian, and finite semi-simple, and the endomorphisms of the tensor unit is just the field C. And then it needs to have a pivotal structure, so an isomorphism from taking the double dual to the identities, and the left and right traces need to agree. So examples, the simplest examples are vector spaces graded by finite group G and equipped with a cocycle. Then there are also representations of finite groups, and more examples can be constructed from quantum groups, or just from other Hopf algebras. Okay, and then how does the Toraev-Vero-Barrett-Westbury state sum work? So one assigns to oriented edges simple objects, and I'll always denote this by the letter L for labeling. And we don't just take any simple objects, but we pick a set of representatives I of the simple objects, and we assign this to an oriented edge, and if we reverse the orientation of the edge, we take the dual object. Then this labeling assigns to each oriented triangle a morphism space in the spherical fusion category. So we can here have two orientations, and here we have the edges that are labeled already by simple objects, and depending on the orientation, we take the morphism space that goes from one of the three objects to the tensor product of the other two. And they're just tensored in the order of the arrows. Okay. To an oriented tetrahedron, this now assigns a 6J symbol or an F matrix. So here we have 6 edges that are labeled by 6 simple objects, and we have 4 triangles that are labeled by morphism spaces. And what we do is we start with one of the triangles, let's say the ABK triangle here, then we take a morphism in the associated morphism space. Then we take the next triangle and take another morphism, then altogether we have 4 morphisms, and this gives us an endomorphism of some object here, and then we take the trace. So this assigns to any 4 given morphisms a number, and this number is constructed as shown here. So we go from B, the morphism beta, to A tensor K, then we are here. Then we go to I tensor J in brackets K. Here we need to apply the associator. And then we go here, we couple the J and the K to the C, and then in the end we go back to the B. And then we take the trace. And for the tetrahedron with the opposite orientation, there's also an opposite 6J symbol. And the Toraev-Vero-Barrett-Westbury state sum then takes this triangulate three-manifold plus a labeling at the boundary with simple objects and a labeling with morphisms associated to the boundary triangle, and computes a number as follows. So we take the product over all the 6J symbols assigned to the labeled tetrahedra. We take the product of the dimensions of the objects on the edges. So here the dimension is just the trace of the identity morphism. Then we sum over all the labelings that assign simple objects to the internal edges, and we sum over dual bases of the morphism spaces associated to all the internal triangles. And then we have some normalization factor by the dimension of the spherical fusion category. So a priori, this depends on the labeling with simple objects at the boundary and the boundary morphisms, And one can also see this as a map that depends only on the boundary labeling of the simple objects and takes the associated tensor product of the morphism spaces at the boundary and goes to C. Okay, so that's the way to construct the Toile-Viro-Barrett-Westbury state sum.
Sorry, what is B?
So here I want to distinguish the L, that is the labeling with the simple object at the boundary, and the B is the labeling with morphisms at the boundary triangles. And in the second formula it's not there anymore, because instead of labeling I see it as a map from the tensor product of all these spaces. Okay, and this is a topological invariant. How can one see this? So it depends only on the boundary triangulation and the boundary labeling. And it's compatible with gluing. And if one takes a certain limit over the boundary triangulations, one then obtains the ground state. And what is behind this topological invariance is essentially the pentagon relation for the associator and the invertibility of the associator. But I'll explain this later. So here I wanted to show it with a simple example. So we take as a spherical fusion category the category of vector spaces graded by a finite group G and with a cocycle omega. Then the simple objects are just the group elements of the group, so we label the edges now with group elements. And the morphism spaces are largely trivial, so they're either the complex numbers or they're just zero. And which of the two depends on if the group elements, if the ordered product is 1 or not. Then if we consider a tetrahedron, and we can choose 3 of the 6 edges, we can choose the labels freely, but then if we want to get something non-zero, the labels on the other edges, the blue ones, are determined. So there's not much to compute there. And what one gets is the 6J symbols. They're given by this cocycle, the cocycle omega. So it's just the cocycle applied to 3 of the elements labeling the edges, or its inverse. And the idea is now that we want to generalize this to a state sum with defects. And then we want to show triangulation independence, and we also need a graphical calculus. Okay, are there questions? Okay, so if we want to talk about the defects, so we have to first say which type of defect we want to consider. So we want to have again a 3-dimensional oriented piecewise linear manifold with a boundary. And within this manifold we want to have defect surfaces. So a 2-dimensional oriented manifold, and it can have a boundary, but the boundary needs to be contained in the boundary of the 3-dimensional manifold. And I call this the defect surfaces. Then on the defect surface, we want to have defect lines and defect points that should form some directed graph that is in the surface. And now the idea is to label this with appropriate categorical data. And what appropriate categorical data is already known, for instance, from the article by Kitaev and Kong. So the regions, the connected components outside of the defect surfaces, they should be labeled by spherical fusion categories, as before. But the difference is now that we can have several spherical fusion categories, not just one. And the defect areas, so the complement of the graph in the defect surface, we want to label this with bimodule categories. And because everything is defined in terms of 6J symbols, which are in turn defined by a trace, we should require that the bimodule categories have a bimodule trace. I'll explain this later. And the defect lines, the edges of this defect graph, should be labeled with bimodule functors, and the defect points, which are the vertices of the defect graph, should be labeled by bimodule natural transformations. Okay. So here I've illustrated it with the picture. So we have CD bimodule categories, M, N, and P. They correspond to the two-dimensional parts of the picture. Between them, we have defect lines that are labeled with bimodule functors. And between the defect lines labeled with bimodule functors, we have a defect point that is labeled with a bimodule natural transformation. Okay, so what is all this data? So I wanted to sketch this briefly. So the bimodule categories with the bimodule traces for fixed spherical fusion categories C and D, they form a pivotal 2 category. So the objects are the bimodule categories. So a bimodule category is a category which here we take to be finite and semi-simple, M, together with 2 functors that describe the action of the spherical fusion categories. So it's like a group action, but it's an action of a category. And therefore, the usual rules that tell you it doesn't matter if I first multiply the group elements and then act, they take the form of coherence isomorphisms. So we have 3 coherence isomorphisms. So one that tells me it doesn't matter if I first tensor within the category C and then act, or act twice individually. Then another one that plays a similar role for the category D. And then another one that tells me it doesn't matter if I first act with C and then with D, or the other way around.
So you can ask,
Yeah?
so what is the difference between considering the state sum with defects and exhibiting the DFT as a 3-to-1 DFT?
The difference is not in the categorical data, but it's in what kind of functor do you want to have? Do you want to have like just a functor or a higher functor? And also you would not admit like any of this data, but you would admit specific choices. And here there's no invertibility condition or dualizability condition, it's just this data. Okay, so that's the bimodule category, and the bimodule trace is defined similarly to a trace in a pivotal fusion category. So it's just a collection of linear maps from the endomorphism spaces of an object M to the complex numbers that is cyclic. So it has the usual cyclic symmetry of a trace. It defines a non-degenerate pairing between the morphism spaces. And it is also required to be compatible with the action of the spherical fusion categories, in the sense that it shouldn't matter if I take a partial trace and then the module trace, or if I just take the module trace for the acted on object. Okay, the one morphisms are C-linear, exact, that's automatic in this case, CD bimodule functors. So that's a functor equipped with 2 coherence isomorphisms. One that tells me it doesn't matter if I first act on the left and then apply the functor, or if I first apply the functor and then act. And another one, T, that does the same for the right action. And the 2 morphisms are bimodule natural transformations. So there are natural transformations between such functors that are compatible with the bimodule structure. And the compositions are just the compositions of functors and natural transformations. The duals are given by the left adjoints of the functors, which in this situation, due to their exactness, are also right adjoints. And they're given by the usual co-evaluation for an adjunction. Now one can look at a simple example. If we take for C and D vector spaces graded by finite groups, now with the trivial pivotal structure and cocycles, then the indecomposable bimodule categories are just sets equipped with actions of the 2 groups that are transitive. And the bimodule functors are given by representations of certain action groupoids. And the bimodule natural transformations are morphisms of such representations. So in this case, one can really compute in a very simple and efficient way with this data.
Don't you have to choose a 2 cocycle?
I've said I choose which 2 cocycle.
Yeah, on subgroups then, on the sets.
So here I've said I choose it, and I choose it to be trivial. On the sets, I can choose a 2 cocycle, but I also want to choose it trivially. If I choose the 2 cocycle, it doesn't change much, it just makes the formulas more complicated. One gets here something like projective representations of action groupoids. So it doesn't change much. Okay, so that's essentially the data, and now is the question how to handle this data and how to use this data to define a state sum model. And because the data is quite complicated, one can do this with the diagrammatic calculus. So the diagrams for this pivotal 2 category are constructed in several steps. So the first step is I can just consider diagrams for the 2 category cut. So if I do this, then like all the regions in the diagram are labeled by categories, here M, N, and P. The dashed lines are labeled by functors, and the dots are labeled by natural transformations. Here I don't admit any functor, but I restrict to CD bimodule functors, and I don't admit any natural transformation, but I restrict to CD bimodule dots. So every line is labeled by a functor that goes from the category on the right to the category on the left. Then putting lines next to each other is the composition of functors. And then we have bimodule natural transformations that are read from top to bottom. So it goes from the functor on top to the functor at the bottom. And here rho, for example, it goes from F to the tensor product of G and H, which is just the composite. And then, if we have such a diagram, we can evaluate it. For this, we can just take horizontal slices. Each slice has either a composite of functors or a composite of functors and natural transformations, and then we compose them from the top to bottom. So here we first have F sigma, because F is on the left of sigma. Then we go down. Then we have rho L, because L is on the right. And then we just compose them and get a natural transformation from the functors on top to the functors at the bottom of the diagram. And here, one has an additional thing. One can move the natural transformations on the different components past each other due to naturality. So I could pull the rho up and push the sigma down, and then I would also get the same evaluation. So the duals are just the left adjoint, which is also right adjoint, and the co-evaluations, they are depicted in the usual way as maxima and minima. The only difference is that here we have labels to the left and the right of the line. And they also satisfy the usual snake identities, so that's just the defining identities of the adjunction. So that's the first level of diagram that has just the bimodule functors and the bimodule natural transformations and the bimodule categories. Pivotality I've forgotten. So the fact that it's pivotal is also depicted by the usual picture. And now to make really diagrams that make these functors and natural transformations interact with the spherical fusion categories, we overlap them with diagrams for the spherical fusion categories. And we choose the convention that the diagrams for C go over everything and the diagrams for D go under everything. And then we can integrate them into the picture by interpreting them as functors and natural transformations. So here we have some diagram of C that is located on a region labeled by M. And then we see the objects of C just as functors that give their action on M. And we see the morphisms of C as natural transformations between such functors. So we can just integrate them into the picture in that way. But if we overlap such diagrams, there can be crossings. So not arbitrary crossings, but crossings of a diagram for C and one for D, diagram for C with functors or diagram for D with functors, and we have to say what we do with these crossings. So here we have three types of crossings. A CD crossing is labeled with the coherence isomorphism that relates the C, that exchanges the C action and the D action. Then we have a crossing between C diagram and the functor. Here we use the coherence datum for the C module structure of the functor, the compatibility between the functor and the C action. And the last one, we have a crossing between the functor and the D line. We use the compatibility isomorphism for the compatibility of the functor with the D action. So these are the three types of crossings that can occur, and that's what we label them with. And then it turns out one has identity just as for braided monoidal categories. So we have naturality conditions, so we can, the naturality condition on these coherence isomorphisms allows me to slide morphisms or dots on the lines for C over a crossing. Then the conditions on the bimodule natural transformations allow me to slide dots on a functor line over and under the crossings. Then we have something like a colored variant of the Reidemeister 2 move. That's just the invertibility condition of the coherence isomorphism. And we have something like a colored variant of the Reidemeister 3 move, which comes from some axiom on the coherence isomorphisms. Okay, so now we can combine these three data in a diagram. Now we want to evaluate such a diagram, so we want to do something like for the 6J symbols, we want to take them and make a number. For this, we put them into a box and label the boundary segments with objects in the adjacent category and the line endpoints with morphisms. So here I've given such an example of the diagram. So we have four different categories, M, N, P, and Q, and then we pick objects of these categories and label the boundary segments. And then the line endpoints are labeled with morphisms. And the convention is always it's a morphism in the category to the left. And here, so alpha goes from the label N, that is to the left, to the image of the label on the right under F. Similarly for beta. And at the bottom of the diagram, the directions are reversed. So here the gamma goes from the image of M on the right to P prime and so on. So once we have labeled this, we can cut open this box and kind of straighten its boundary to a line. And then we can define an evaluation. So if we cut it at the object N and straighten it to a line, we get a diagram like this. And this we can easily interpret. We see on this boundary line, there are objects of the bimodule categories. Then we have these lines in the interior or to the left, they're labeled by functors. And how we interpret this is simply the functor lines on the left are applied to everything that is on the right. And the vertex labeled by natural transformation, one takes the component. So here we go from N with alpha to F of P. Then here the F is also applied to the beta. Then we go to Fk of M, then we are here. Then we put the component of sigma at the object M, and so on. So we have a way to evaluate it. And then we have the same object at the top and bottom of the line. So it's an endomorphism of an object, and we can take the trace. So I denote this by these horizontal bars. So in this way, one can assign to any kind of labeled rectangle with a diagram inside, we can assign a number. And the properties of the bimodule trace and the pivotal structure tell me that this number does not depend on where I cut the diagram and is invariant under rotations. So what I could do is I could take this line, this label gamma here, and kind of slide it here until it is at the top. Or I could take the label alpha and slide it down until the line comes here to the bottom, and this would give me the same evaluation. So this is really something that does not live on a rectangle, but on a disk. Yes?
Wait, so could I think of this rectangle as a domain wall separating the because it's described by C and D?
Yes, yes, that's what they're supposed to be. So they are co-dimension 1, so a domain wall. Yes, and like in the two-dimensional models, this plane would become a line because it intersects something two-dimensional. Yeah.
And within this domain wall, there are these different regions like NPM, which would be like different kinds of domain walls.
Yes, you would have like, you could see the MNPQ, and you could see them as different domain walls, and you have domain wall junctions between them, but here I restrict attention to bivalent junctions, so only 2 categories. Yes, that's...
Can I ask also a very naive question? Apologies. You started by saying that we are trying to compute the code space of surface codes, Kitaev's code, or did I get this wrong? So, is this valuation doing this now?
No, not yet.
Not yet.
Not yet. So first, like you would imagine that the boundary of such a two-dimensional surface that I'm considering here would give you a line, and that would be like the boundary part would belong to the Kitaev code. So this is in the three-dimensional one. So it's a two-dimensional thing that sits in a three-dimensional theory, and if you intersect this two-dimensional thing with the two-dimensional boundary of the three-dimensional theory, then you would get a domain wall, which would be a line between different faces. But it's meant to help computers, yes.
Okay, maybe I'll ask again.
Okay. But here I see it really as something two-dimensional that sits inside something three-dimensional. So one would maybe say it computes the time evolution of this space.
So you're not going to show the actual result?
To show it exactly how it works?
Yeah. Do you comment more on this?
I'll comment a bit more on this later, and I can also do it on the blackboard. But I haven't said even how to compute it in the three-dimensional case. Okay. So these polygon diagrams or disk diagrams, they satisfy some cutting and gluing identities. There one can fix some representatives of simple objects for the spherical fusion categories and also for the bimodal categories. And then the polygon diagrams, they satisfy some cutting and gluing identities. So the first is I can glue 2 polygon diagrams along a side by summing over the morphism spaces. And then the evaluation is the same as the evaluation of the diagram on the right. So here I have 2 diagrams with 2 evaluations, and if I multiply the evaluations on the left and sum over the dual basis of the morphism spaces, then I get the evaluation of the diagram on the right. Then one can also glue along a vertex. So here we glue these 2 adjacent sides so that this tip here labeled N goes into the interior of the diagram. Then I can just kind of glue it together. And what I need to do here is to sum over the morphism spaces and also over the simple objects N that disappears in the interior. And here the dimension of N is defined as the trace of the identity morphism. And finally, one can also take a two-gon and glue it to a sphere, which is the picture here. And what one gets here is just the dimension of the bimodule category times the graph that I get when I glue here the top and the bottom. And these are essentially and the dimension is the sum over the dimensions of all the simple objects squared. And there's another identities that allow me to paste spherical fusion category data into these polygon diagrams. So why is this important? These cutting and gluing identities are also used, for example, in topology to make up surfaces out of polygons. So this tells me how I can just take polygons, glue their sides pairwise, and make out of this a surface. And this data, this pasting spherical fusion category data tells me how the surface will interact with the spherical fusion categories on the 2 sides of the surface. Okay, I can use this now to define the state sum model with defects. So I take some oriented 3-manifold with defect data and I take a generic and transversal triangulation. So what this means is that the triangles in the triangulation should intersect the defect surface in lines with endpoints on the edges. The defect surface should intersect each tetrahedron in a polygon with endpoints on the edges. We don't want vertices of the triangulation on the defect surface. We don't want edges of the triangulation to intersect defect lines. And we don't want defect vertices inside the triangles. So basically it means that the defect surface can only intersect a tetrahedron in 2 different ways. Either it intersects it in such a way that there's 1 vertex on one side and 3 vertices on the other side, or it intersects it in a way that there is 1 edge of the tetrahedron on one side and 1 other edge on the other side, and the remaining 4 edges intersect the surface. So this is similar to generic in knot theory, for example, where one wants to choose a projection such that it is nice. Here we want to have the triangulation in such a way that it's nice and it doesn't sit awkwardly on the defect surface or the defect lines. Okay. So then essentially we have these 2 pictures. I mean, what we could have here, of course, is far more functors, G on this side here, and here we could also have more lines and so on, but we could combine them into 1 line by taking the tensor product. So essentially these are the 2 diagrams one needs to understand. And what we see also in these pictures, because the planes or the defect surfaces are oriented, all these edges that intersect the defect surface, they inherit an orientation. And the other edges are arbitrarily oriented. Okay, now we need to label this. We can think that the edges that are not intersecting the defect surface, we label them just as before with spherical fusion categories, and the edges that intersect parts of the defect surface, we label them with objects of the associated category. So here we see these black edges that do not intersect the defect surface. They are labeled with object of the spherical fusion categories, but these colored edges here intersect the defect surface and they are labeled with objects in these categories here. So we label with 2 things, simple objects in spherical fusion categories and simple objects in bimodal categories. And to the oriented triangles, we can then again assign morphism spaces, and these morphism spaces depend, of course, on the data. So the morphism space will be different if there's an endpoint of a defect line in the triangle. And to a labeled tetrahedron, we can then assign a generalized 6J symbol. So how is this constructed? So first, that the pictures are nice, we construct for the triangles that do not intersect the defect surface, we take the dual. So here, instead of this triangle, we take a vertex, and dual to each edge, we construct an edge. And here also we are taking the duals. This is just so the pictures are nice. And then, after taking these duals, we can project it. So we can project everything in the tetrahedron on the defect surface. So for the first tetrahedron on the left, this gives us such a picture, and for the tetrahedron on the right, this gives us another picture. And these are the 2 pictures which we can evaluate with the diagrammatic calculus, and they give us a number. So they're just polygon diagrams, we can cut them, and we can evaluate them, and this is what we define as a generalized 6J symbol. And they give us a number that depends, of course, on all the morphisms that are labeling the vertices here, and on, of course, on the objects that are labeling the edges, and also depend on the functors here. Yeah, and one can show that this is independent of the choice of orientation of the edges that do not intersect the surface. Because there's an arbitrary choice for the edges that intersect the surface, it's not a choice, it's given by the surface. Okay. Yeah, so why do I call this a generalized 6J symbol? Because one gets a special cases, one gets the coherence isomorphisms for the bimodule categories and bimodule functors. So this is the first generalized 6J symbol I've drawn. The simplest thing one could do is one could maybe say, let's make all the dashed lines trivial and label them by identity functors. Let's make the vertex labeled new also disappear. It's the identity natural transformation. And let's maybe take all the colors to be blue. We take just one bimodule category. And then one gets this picture here. And this 6J symbol represents the coherence isomorphism that is related to the C module structure of my bimodule category. And as a special case, I could take, as the bimodule category, I could take C itself with the left action from the tensor product, and then I would just get the associator of C. And similarly for the other 6J symbol, so here I could also take all the dashed lines to be labeled with trivial functors. Then I would get this picture here. And then this picture here represents the coherence isomorphism that relates the left action and the right action. And again, I can take the category C as a bimodule, a spherical fusion category as a bimodule category with the tensor product. And then this represents the associator. And similarly, we can now also decide to take the lines labeled by C and D trivial and to keep some of the lines labeled by functors. Then one gets a 6J symbol that describes the C module functor structure, and one gets a 6J symbol that describes the D right module functor structure. Okay, and one could of course also call them generalized F matrices. And the most generalized F matrix on the left is kind of a superposition of all of those. Okay, now one can define the state sum. So we can take a 3-manifold with defects and a generic transversal triangulation, and we label them. So we label the boundary edges with simple objects and the boundary triangles with morphisms. And then we can define the state sum exactly as before. So it's a complex number that depends on all these labelings. And it's given by taking all the generalized 6J symbols and multiplying them together, multiplying by the dimensions of all the edges in the triangulation, summing over the assignments of simple objects to the internal edges, and summing over bases of the morphism spaces for the internal triangles. The only thing is different that now the 6J symbols are generalized 6J symbols, and this combines data from different categories. And the normalization factor also changes a bit accordingly. And again, we can also see this is a map that depends only on the simple objects labeling the boundary to the morphisms, from the tensor product of the morphism spaces for the boundary to C. And from the definition, one sees directly that this gives the usual Torah-Viro-Barrett-Westbury state sum without defects if one has no defects. Because then just the 6J symbols become the usual 6J symbols, the dimensions become the usual dimensions, and everything reduces to that case. And one can also show in a fairly simple way that this is compatible with gluing. So if we take two manifolds and glue them together, we have a construction that tells us what to do with the state sum. Okay, now the hard thing to show here is to show that this is really independent of the triangulation. And this I will only sketch how one can do it. So one can consider what I call a fine neighborhood of a defect surface. So this should be a generic transversal triangulation. The boundary of this 3 manifold should be intersected with the defect surface, should be the boundary of the defect surface, and all the vertices are in the boundary of M. And all the edges and triangles that do not intersect D are in the boundary of M. So here I've sketched this. So basically we have triangles and we have tetrahedra. All the tetrahedra intersect the defect surface, and the triangles that do not intersect the tetrahedrons, the defect surface, they're just in the boundary. So it's like a small interval times the defect surface. So it's forbidden, for example, to take 2 of these triangles in the boundary and just glue them together. The only things that are glued are the things that intersect the defect surface. And one can show that if a 3 manifold shells to a fine neighborhood of the defect surface by via tetrahedra that do not intersect the defect surface, so this means essentially I can make it into such a neighborhood by adding or removing tetrahedra that do not intersect the defect surface, then the state sum is given by projecting the dual of the triangulation to the defect surface. Like in the picture above, this would give me this. Cutting the defect surface to a polygon diagram, and then evaluating this polygon diagram and summing over the objects and morphism spaces for the vertices and sides of the polygon that are supposed to be glued. And this can be shown in a fairly simple way by induction over the number of tetrahedra in the triangulation and the possible way of gluing them, and by the cutting and gluing identities for the polygon diagram. And this shows already that this is invariant under Pachner moves between generic and transversal triangulations. And this is simply because they are fine neighborhoods of defect disks. And the boundary triangulations agree. So here, the Pachner moves are usually used to show triangulation independence. So if one doesn't have any defect surface, one would just have the moves A and B. A takes 2 tetrahedra that are glued along a side and changes it into 3 tetrahedra that are glued along an edge. And the move B subdivides 1 tetrahedron into 4. And one can show that all different triangulations of some 3-manifold M without boundary are related by such Pachner moves, by a finite sequence of these moves A and B. So if I can show that something is invariant under these moves that is defined in terms of a triangulation, I know that it doesn't depend on the triangulation. And what one can show is that there are analogous Pachner moves. If I have surfaces with defects in them, that's the entire list. And that's a consequence of this last statement, but it can also be seen as a consequence of the properties of the coherence isomorphisms for bimodule categories. So it's not practical to give a full list of this. This was just for bimodule categories, but one gets the idea. So here, one has invariance under Pachner moves, as long as the associated triangulations are transversal and generic. However, this doesn't always happen. You can also do a Pachner move and later the triangulation is not transversal and generic. Then you have to do some more work. And indeed, one can show that for any 2 generic transversal triangulations of a 3-manifold with defects, such that the triangulations coincide on the boundary, the state sums agree. And the proof is essentially by subdividing it. So one subdivides it with stellar subdivisions so long until the tetrahedra that intersect the defect surface form some fine neighborhood of the defect surface. And one knows that if such fine neighborhoods, so in different triangulations, these fine neighborhoods are PL homeomorphic and they're related by schellings. And these schellings just paste spherical fusion category data on the polygon diagram and then relate the state sums. And in the complement of these fine neighborhoods, one just has the usual Toralf-Vero-Barrett-Westbury state sum without defects. And one can then piece it again together by gluing these fine neighborhoods and the complements. So this is roughly how one can show that the two state sums agree. It's not practical to show it just with Pachner moves due to the many different types of Pachner moves, and also due to the fact that the Pachner moves can destroy the statement that the triangulation is transversal and generic. So it's not simply doing Pachner moves as one does before, but one has to work a bit more. Okay, and then one can define the state sum for non-generic or non-transversal triangulations by subdividing to generic and transversal ones. And in this way one can show topological invariance and that it depends only on three manifolds and the defects, but not the triangulations. Okay, so now I wanted to give some examples. So the examples are mostly three-dimensional, but I think they illustrate what is going on. So on one hand, one could consider some defect sphere in a ball. So we have a tetrahedron outside, and then we have a little defect we subdivided into four, and then we have a little defect sphere in the interior of the tetrahedron. And then for any bimodule category M that we put in the interior, the evaluation of this is the evaluation without the defect times the dimension of M divided by the dimension of D. So D is the spherical fusion category in the interior. Yeah. One can also consider some sort of cylinder on a defect surface. So we can consider a surface times some interval, and we place the defect surface in the middle. And here one can compute explicitly, for example, in the case where one labels the surface by bimodule categories over fusion categories graded by finite groups. And these bimodule categories are given by finite transitive sets. And here one can simply compute it by using prisms and then evaluating the associated polygon diagrams. And what one finds is that this, the state sum is zero unless the boundary labels define some group homomorphism from the fundamental group of the surface into the two groups. And if they do, then the state sum simply gives the number of fixed points under the group action. What one can also do is then kind of vary the type of defects one is using. So here one uses a finite transitive set with group actions. One of the simplest things one can do is just to say the group are equal to each other and also to the set. And the group just acts by left and right multiplication. Then one gets the requirement that the two group homomorphisms on the two boundary must be conjugated. And what one gets here is a stabilizer group of the group homomorphism. What one could also do is to make the defect really strong by taking a one-point set on which the two groups act. Then one basically disconnects the two sides of the defect surface. And then one simply gets that the state sum is 1 for all the different group homomorphisms that one could pick. What one can also do is construct a compute for a genus G defect surface in 3-ball. One just needs to decompose it appropriately, and one can really, at least for the case where we have bimodule categories over vector spaces graded by groups, and the bimodule categories are given by sets, one can really compute it explicitly, and one sees again, so what one gets is the state sum without the defect on the right-hand side, multiplied by some factor that is the number of elements in the sets, then the certain powers of stabilizer groups, and so on. So this example shows already that it can detect to some degree the genus of the surface. What one can also do is knots. So one can consider a torus embedded in S3 that's labeled by a VEC module category, VEC G module category, and we can take the set to be trivial. And here one can then compute it, and one sees that one gets the number of group homomorphism from the knot complement into G up to conjugation. So at least for simple categorical data, one can compute this rather easily. What one can also see is ribbon defects. So we can take a spherical fusion category as a bimodule category over itself, and then the endomorphisms are the center. Then we can take defect surfaces also labeled by C, and then the line and point defects are labeled by the center. So in this way, we can construct a ribbon link as a defect in a 3-ball, and a ribbon link labeled by the center of C. And what one sees is that if one has the defect, one gets what one had before times the evaluation of this ribbon link by the center of the spherical fusion category. One might wonder, how does one get the braidings in this? The braidings in this link diagram evaluation come really by gluing tetrahedra. Yeah. So here one can see, here one has one bit of line and another bit of line, and one glues these 3 tetrahedra together as indicated by the labeling. So this one goes on top, then this one is the second one, and this one is the third one. One can evaluate it, and then one gets a 6J symbol that looks like this. And here one sees already the crossing. So this is the braiding for the center. It comes up in this way. Okay, so thank you for your attention.
So in these results where you relate a partition function with the defect to something without the defect, is that coefficient? Can you say something about that coefficient? Like, is it always greater than 1 or less than 1?
I think to say it's greater than 1 or less than 1, this I cannot say. I mean, what I can say is that it gives some sensible data. So if I place a defect inside, a defect surface inside a ball, I would expect that I get some information on the genus of the defect surface. And here, if I place a link inside a ball, for example, I would expect that I get something like a link evaluation for this data. So here I could not say if it's a link evaluation for the center, then okay, it's a number, but is it greater than 0 or not? That will maybe depend on the link. So what I can say is it encodes some geometrical data that seems sensible, or that you would expect it should be there. And in this case also that one knows it should be there because this was treated in a different framework by Prof and Virelisi. And it gives what they got.
So you had generalized 6J symbols. For some people in this audience, these are interesting as tensors in tensor networks.
Yeah.
You have coherence between them. Yeah. What kind of generalizations of pentagon equations and this do you get in this?
You want me to write down the coherence isomorphisms?
Do you have something like pentagon relations?
Yeah,
with
yeah.
6J symbols?
Yes, you could say you have pentagon relations that are expressed in the Pachner moves in the presence of 6J symbols. So one example. So this was on the slide before. So we can have like a picture where we have a tetrahedron with the defect surface inside like this. And now we could apply, so here we have 2 tetrahedra glued along a triangle. And now we could apply a Pachner move and change this into 3 tetrahedra that are glued along a line, also with defect surfaces. And here we would have the 6J symbol for the bimodule category structure. And what it would give you is so invariance under this Pachner move that I'm discussing would correspond precisely to this relation that one has. So for a bimodule category. So it's some relation where you have something like this, and then you could now, here you could change it to C acts on C prime, acts on M, acts on P. Here you could rebracket it, and you could do C tensor C prime, acts on M, and here you have D. And now and then 1, 2, 3, 4. So what is missing? Ah, here. And here I've forgotten a bracket. Yeah, here's the missing bracket. So this would be like a pentagon. And pentagon always means it has to do with partner moves because it's a 2-3 partner move. So 2 tetrahedra, 3 tetrahedra. And the defect surface just stays where it is. And therefore you know already that this relation must give you a 2-3 partner move. And all of the relations in a certain way give you partner move invariants, the ones for the functors. You have defect lines here also, and you need to set some data on the edges that do not intersect to the unit. So you can really make a dictionary how like all the coherence isomorphisms that you have translate into a picture that gives you invariants under some partner moves. And that's, I think, is. So I don't know how to translate it into this other picture where one is on a surface, but here it is encoded in the partner moves, and I think this should have a similar description on the surface. Yes.
Can I ask again? I'm sorry, my physicist's question. So suppose I'm given something like Itaev's code, and I want to calculate an entanglement entropy in the ground state. Can I do it with this?
Yes, so you can take a surface. So I'll do it for the case where we have vec G, okay? And then we have vec G, and we have vec G prime, and we have M is a G times G prime offset. What you can do to compute what is on a surface. So you consider a surface that is triangulated. Is there some color chalk? Yes. Yeah. So you take a triangulation of the surface. And then on the surface you now have maybe some defect lines. Right? So here you have maybe the group G, and here you have the group G prime, and here you have the set M. And what you can do is now you color all the edges. Here you color them red that intersect here. And you label them by elements of the set M. Here we have M prime, and here we have M prime prime, and here you label by group elements. And then you can define the vertex and the plaquette operator in a way very similar to before. So what the vertex operator, what happens here, so usually your vertex operator, when you have a vertex with say G prime and G prime prime, let's call this H, then it sends this to HG, G prime H inverse. No, this was outgoing also, so it's GH inverse and H G prime prime, right? And now if you have a colored edge, here, so if we now change this, and this is an edge labeled M, so what can so here then I don't have this orientation, I have only an orientation here, so what can let's maybe put it this way. So here, what can I do now if I have a red edge M? So I can no longer just left multiply with G, but what I can do is I can act. And this is how you define the vertex operator. And for the plaquette operator, it's similar. So usually you would have a triangle, you have a condition. So the plaquette operator imposes this, right? Well, if you have a colored triangle, it cannot be arbitrarily colored. It will always have two colors that point to the same vertex. And here you would just ask that M prime is G acts on M. So from the arrow orientation, I can read this out. And here it's of course crucial that you don't have a tricolored triangle, but tricolored triangle cannot arise because this is here. Tricolored triangle can only happen if you have a defect point in the interior. Yeah. And with these, you could have a triangle like this. But this would mean that you have a defect line here, and you have a defect line here. And you have the red defect line that comes here. And here you would have, at the vertex, you would have, so these are then different sets, and here you would have a representation of an action groupoid. And then this representation of the action groupoid would tell you what vector space to associate here. So in the case of Dijkgraaf-Witten, or the G-graded vector spaces, you can make this very explicit, and I can really write down this quantum double model. I think I'm out of time, so I shouldn't do that.
Thank you very much.
Thank you very much again. So, thank you very much again.